supposed to say recording on the
Okay, I am now recording. Okay.
Martin, you just why did you just spoil the entire lesson? But all right. Martin
Okay,
just spoiled
whatever.
the entire lesson. He's like
Bro, okay.
nice one.
This is hard, okay.
Yeah, it isn't hard. It's more to like get down the understanding and then to understand more complicated algorithms. Like because if you know what binary search is, you'll obviously understand asymptotic growth really well. But even if you don't, you can still understand it. You don't need to be Martin and be super smart and like already know what binary search is. Don't worry if you have no idea
Very
what it
big
is though.
brain. You need to be
Yeah,
very big brain.
very big brain. All right, Martin. Since you're very big brain, how many guesses would it take? The smallest number, the last number of guesses.
What is up with okay? I don't even know what's up with this anymore.
Do you want to just do you want me to just do it? It's just an extra slide.
Yes. Okay. Has everyone got a chance to like play the game yet?
Yeah. And also, does anybody want to put in the chat what you think the least number of guesses is? Or what is the least number of guesses you got in the game? 6. Wow, you can get in 6 guesses. That's insane. Wonder how you did
Very
it.
good.
Very cool. I mean, not just for a computer though, like also for a human, because you can also get the least number of guesses without even using a computer, right?
Yep. So should I move on then?
Sure.
Okay, because I can't
Cool.
really see the chat right now. Oh god, computer sucks. So there is a naive strategy, which is obviously where we would just guess every number from 1 to 100, and we want to convert this problem using the known data structure we had taught you previously to say try to write a program that would solve the or play this game with the existing program. So obviously I said that naive strategy would just be guessing from 1 to 100 all sequentially, and it would take 100 tries. But there's clearly a better strategy that once implemented is much faster than guessing each number by itself.
One thing Matthew didn't mention was the previous slide. The reason I did 2 slides is that the first thing you actually had to try to do was to convert the question to a given known data structure, right? Because if you just try to guess a number between 1 and 100, it's not really a valid question. Like you don't really know what to do with it. And the first thing you should actually do is to convert it to a known question, which is an array. Because if you or a list, because when you put it all the numbers in a list, now you can actually do some sort of search. If it's just 1 to 100, it's really abstract, right? You don't know how to actually search, but now you know how to search a list, which is good because we might use that to our advantage. But basically, the simplest way to search a list, like Matthew said, is to just do linear search.
So if someone has a better strategy, just try putting in chat right now, and I guess Jerry will mention anything he finds important. All right. So
Is there a
if
better?
you have a strategy, just put in the chat, and I'm
Yeah.
just going to be moving on for now. So that's basically what I just did. Ask for optimal strategy. Well, before I asked for better strategies, but now we're looking for the optimal strategy, which is something which I'm not going to tell you yet, but you can just put in the chat.
Or even if you don't actually have the optimal strategy, you have like a strategy that you think might work, you can put it in. And Martin, you can explain whatever binary search means now if you want.
All right. So I'll give people can still write their answers, but now I'm just going to move on. Like actually move on, I believe. So now we're going to talk about what's the actual optimal strategy, which is basically you always go for the middle of the possible range. So like from 1 to 100, you would first guess 50. So now if we know it's higher or lower, we automatically just remove half of the possible answer as a possible choice. Okay, that might have been a little hard to understand, but basically we know that now half of the answers are not correct. And then we just keep going through the half of the possible range to eliminate half of the possible answers. And we just keep going until we have our final answer. So obviously this method is called known as binary search. And you can see it's guaranteed to solve within 7 to 8 guesses, or log 2 to the power to 100. Wait, no, I said it wrong. Never mind. It's log base 2, 100. So if you have any questions, just put in a chat, and Jerry will answer any relevant questions you may have.
Yes, and I also have a preface. I have another thing to add for this. Basically, it's not a lot to add, but basically, when you're actually going through this range, there's one thing to consider is that you also have to consider what happens if you actually got the answer. Like basically if you're thinking about the actual like implementation of this, like if the secret number is lower, you can do something. If it's higher, then if it's then equal, then you should also do something. Another thing is that the smaller half of the range actually sounds kind of weird, which I want to talk about that. Maybe I'll explain that more later. But basically, smaller half you can actually not even check the smaller half. You can just include the number that you guessed, and it will still work. If you check the smaller half, it might be confusing why it still works, but it still works. It's just easier to understand if you also include a number that you're searching. But sure, cool.
So now we're moving on.
Moving on.
So we're explaining a little bit more in detail, and you have this very helpful infographic and animation here to show you how binary search really works. As you can see that in the binary search, animation is much faster than sequential search because we use an optimized strategy and we don't have to look through every single possibility. So then now we're gonna, so if you well, this is binary search and it's very helpful, and you can see one of the fastest searching methods. And if you have any questions or don't understand, just feel free to put more questions in the chat. Would you like to add anything, Jerry? Okay, I assume that's a no.
Right.
So now we have we have a little situation where say if someone doesn't believe us that binary search is faster than sequential, how do we prove that binary search is faster? Is it always faster? Is there a situation where binary search would be slower than sequential search? So I'll just give you a little time to think about that and say put any answer you have in the chat.
Also, Matthew, can you see the chat at all?
No, unless I leave the screen, I cannot see the chat.
Oh, you can actually do that. Go to like there's something on the right, which is like you can like on the right of like the screen. I think there's something that's like view chat or something.
Oh, great. Mhm. Well, I don't see it, so it's fine. Well, do you want, Jerry? Do you want to read out any of the answers or any comments that the chat has put in?
All right. There's there's one thing. Sequential search is fast if you're looking at the first item, and that's really true. That's actually called the best case time, and we will talk about this when we look at asymptotic growth. But sometimes sequential search is actually slower, and that's you're you're completely correct. It's that sometimes sequential search is sometimes even faster. Worst case ON. Okay. Okay. Let's not get ahead of ourselves. All right.
Oh, okay. So we can tell that sequential search can be faster in certain occasions when you have, say, best case scenario or very close, like the third item and fourth item. But we can tell that generally binary search would be faster overall in a general sense. So now we want to talk about time complexity, which is you would use time complexity to denote how fast an algorithm or any sort of method you use and how fast would it take based on the average, best case, worst case. And we want to use these notations to discuss time complexity as their standard in most in most computer science circles.
Yes. All right. Uh, should I share now, or do you want to stop sharing, or
Uh, okay, guess I'll
because you
just
probably
stop.
won't understand the next slide. It's like crud. I need to explain that anyways.
Oh,
Uh,
all right, if you insist.
all right. So again, a preface from before. It's just this slide I kind of want to preface is that as you can see, binary search actually takes a lot faster than linear search, but only if you're searching from the right side, which is kind of like what Martin said. Basically, again, binary search is when you go from the middle each time. And as you can see, you actually eliminate half of the answers, like at least half the answers every time, which is better, which is technically not better, but it's more stable, right? Because if you think about it, you're getting rid of more solutions every time. So that's kind of the intuition we have for why an algorithm is faster or slower. Oh, by the way, Matthew, it's on the very right called more, and then the first one is called chat.
Oh, I
And then
am
there's
very
also a
smart.
keyboard shortcut. Yeah, so that's the main intuition we have, right? So we know what binary search is. We just go from the middle and then we keep going. Like, as you can see here, we have a low and a mid every time. We low and high, and then in the middle, a mid. So every single time we're going to move the mid around. And then the next question we have is that it's more stable, but is it better? Is it really better? Because if you look at it, if it's like Martin said, the first element, sequential search is better. So then we kind of have our intuition for really needing to understand this question, right? Because we have so many different we have so many different ways of searching, and there are definitely others. But even with two, it's impossible with our current knowledge to compare these algorithms, like which one is faster under which subsets, which one is slower under which subset. Are there places where they're the same? Right? We can't really answer any of these questions without knowing some sort of general algorithm or way to solve this, and we need to define some new notation. And the new notation is called time complexity. And Martin actually put time complexity in the chat again, very ahead. But what time complexity basically means is how fast something runs, and we really care about this in computers. If you go into computer engineering, you learn about computer systems and hardware, and you learn about something called CRUD. What that means is that, first of all, let's talk about how things run, right? So first of all, you have random acts. Let me just move to the next slide, so then you can read it, but you probably won't understand it anyways. We're looking at this. We're looking at this slide. So first of all, what's CRUD? When we have a computer, we definitely have RAM or some kind of memory, right? Some kind of memory, and then we now have the CPU here. And what basically does is that this is very, very simple. This is simplest as you can get, but it basically asks the RAM for stuff, it gives it back, and then does stuff. Basically what it does in a very simple context. It's actually a lot more confusing, but think of it as a CPU basically asks for memory and it does something with it. It basically does an operation. And the most basic operation that a CPU can do is called CRUD. Create, replace something, something delete. I forgot what the U stands for, not too important. But CRUD basically means the most simple operation that a computer can create, because we need some way to define how fast the algorithm is. We can't say, oh, this is faster because it works on an array. An array can't, you can't really judge that. And we actually call this is a branch of mathematics, computer science called asymptotic growth. Asymptotic growth basically measures how fast something can run, because we need this to analyze which algorithm is faster. And even in your ICS3U, even in your ICS courses, your teachers might ask you, well, what is the fastest algorithm, or what's the fastest way to do this? And if you don't know, you're going to be like, oh, this one's faster because it works on this array. That's not a good reason, right? Um, because just because it works on one array doesn't mean it works on all others. To prove something, you have to prove it works on all sets, or at least a certain subset of sets that you define. So first of all, we need this definition. If you get this, that we define any CRUD operation as taking theta 1 time. And what that basically looks like is theta 1. Basically that's what it means. And we also define some more notation. These two will no longer look at omega n, because omega n is a lower bound. Basically, it can get faster. Like omega n is basically a lower bound. Now what that means is that basically omega n is like, okay, so let's say it runs at 3, for example, megabytes per second or something, and the omega n would be 2 megabytes per second, right? So we don't really like omega time, because we don't actually have a good we don't really need a lower bound for the time. We want to know what the worst case is, right? We know that it's definitely above 2 megabytes per second, but we can't know if it's 3 or it's 4, or it could be 100. It could be 1,000,000 megabytes per second, and your omega n might come out to 2. That's why we don't use omega. O time is the one we want. This is the one we really want. And basically, ON is the upper bound. Now let's say the upper bound is 5 megabytes per second. That means that your program cannot run faster than 5 megabytes per second. So if somebody's like, I want 6 megabytes per second, but yours runs at 5 megabytes per second, you're going to be like, I can't do that for you, because my big O time is 5 megabytes per second, so I can't run 6 megabytes per second. It's physically impossible. So now you see how important this notation is when understanding this, when understanding asymptotic growth, because we need a lower bound and an upper bound, but we really only care about this upper bound here. We can throw this away. And what theta is that theta is a very, very bare approximation of the middle. So think about it. If this is omega and this is O, this is now theta. Right? Theta is the middle, or the very bare squeeze between O and omega. Now, if you know the squeeze theorem, you know that this is basically this is between two different functions, but that's not too important. Another important thing is that most computer scientists denote O and theta as the same thing, since they're very similar. What does that mean? That means that O is closer to theta than you think. Omega and theta are close, but we don't really care about omega. But most people just denote O time as theta time, because O time and theta time are very, very close. It's a constant off. And in computer science, we don't really care about the very little distance between O and theta. Because if you look at notations, like for example, this is linear search, and this is binary search. You know what? You want to know what the omega? You want to know what the O for binary search is? It's like for linear searches, it's like this. We don't care. We don't care about these two are essentially the same thing, because log n is like here, and on is here, and theta n is like here. We don't care about these two. These two are asymptotically the same distance apart. When we have this thing that literally peaks off, right? This distance is so much bigger than this distance, which is why O and theta are essentially the same thing. They are essentially the same thing, because we can denote them using kind of the same kind of property, and we can use it to judge exponential time. Now, some anonymous person said this. The reason I said anonymous is because I don't even remember who said this, but this is how I learned asymptotic growth. That someone told me, if you know big O, we know that it can't get any worse than this. And that's how you remember big O time. You don't use the reason because omega and theta time is not as mainstream is because we don't really care. we more want to care about the lower bound. And usually ON also denotes data time, which is kind of weird, but think about it as these two are kind of the same thing. They're not, but they're kind of, like they're close. So we just basically care about this, and we use O because theta is annoying to write, so we use O.
Yeah.
And now the again, but the question begs is that what can we do with this, right? We don't know what this means. All we know what this means is that we know that ON denotes the upper bound for something, how fast the program works given a size. So basically what this means that ON is basically means that if you have something of size n, it will take n time. That doesn't mean anything unless we define what O is, right? So we kind of need to define it. First of all, another preface. Uh, the comment here is that it looks like math. Yes, it does. It looks a lot like math. And um, we can actually use Desmos to graph out some of these, functions. And for example, if we have O here and we have theta here and we have theta here and we have omega here, this is actually a valid theorem. We see that these are really close. These are really, really close together. And especially if you look at theta and omega, these are, theta and these are really close together, right? If we have linear search is like this is way farther away than these two, right? This is way farther away, and it gets farther and farther away, which is why we no longer care about this distance because it becomes arbitrary. Quick note on calculus again, we talked about the squeeze theorem. The squeeze theorem actually is the proof for why time complexity works. If you don't know calculus, don't worry. But if you do know calculus, basically, if you want to use math to try to understand this, you can. If you have fx less than equal to, if you have the fx less than equal to gx, which is also less than equal to hx, we can take the limit to all three of these, and we have lim of fx is less than equal to the lim of gx, which is also less than equal to the lim of hx. And what this basically means is that if the lim of fx and hx, if these two are the same, then the lim of gx is also equal to k. And that's essentially what what O time means, is that O time or theta time is actually bounded between this fx and this hx, right? It's bounded between two different functions, but because they're very, very close together, we can essentially bound this lim gx to a value that works. This all sounds really confusing if you don't understand what this means, but it is very simple if you understand what it means. And even if you don't, it's really important to know a bit of math when you're doing computer science. And if you don't want to memorize it this way, it's really simple to know. Again, just go back to the previous slide and be like, okay, it can't get any worse than this, right? O is the best time. I cannot, my theorem cannot become this. This is not possible, right? I cannot, at the end, have an equation that looks like this, because again, we told you that O is the upper bound. It can't get any worse. All right, so also another preface is that we actually want the time complexity to be as small as possible, not as big as possible. This might be trivial, but I want to explain it because a lot of people are like, oh, we want this to be really big. No, we want it to be small, because the smaller it is, the slower it takes, the faster it takes to compute, right? Because if you have to do one operation, it's really fast. Like if you have to add 1 + 1, but if I tell you to add 1 + 1 10,000 times, like this, now it becomes really hard. Think of it as how many times you have to add 1 + 1. If I tell you to add 1 + 1 a million times, yes, it's still easy. Every time you do it is easy, but you have to do it a lot of times, so it takes more time to do it, right? So we want to take less time, prefer to taking more time, right? And we want to talk about, this is another one. It's a rule. It's called the basic polynomial asymptotic growth rule. And it's called the polynomial, the rule I actually called the polynomial asymptotic rule. It's not really a rule. It's not even necessarily called this, like it's called multiple things, but it's basically a rule of how we can judge asymptotic time, right? Because we want to find the asymptotic time of different functions. And as we get more and more complicated algorithms, we need to start categorizing them based on their asymptotic time. We can't just say, oh, for example, sorting takes some time. It takes as many elements as the array does. We can't really say that, or we can't really say that, this algorithm works fast, because fast is subjective unless we make it objective. So we have to make it objective.
Yes.
Yes. Did
Very
I say
fast
something funny?
algorithm. It's very, yes, like he said, it's very subjective on whether an algorithm is fast or not. And if you happen to hear someone just describe an algorithm as fast, then
Yeah.
they need to do a lot of things.
Yes. I've actually heard people say that like an algorithm is fast.
Like, what does that mean?
Exactly. What does that mean? You have to explain it. So the polynomial asymptotic rule looks really hard. Again, we're gonna make it as simple as possible, just like we did the previous slide. We're gonna make it again. Ignore this if you don't know calculus. I just wanted to talk about it. But ignore this if you don't know. Basically, we're gonna break it down. So let's say you have a polynomial. If you don't know what a polynomial is, basically it's ax to the n plus bx to the n minus 1. Hopefully you know what algebra is, plus cx to the n minus 2. If you don't know algebra, I can explain what algebra is, but this is called a polynomial. Here's a concrete example. So 3x squared plus 4x plus 5. That's a example of a polynomial. If you still don't know what a polynomial is, I can explain it. Please put it in the chat. Otherwise, I'll assume you know what a polynomial is. And what this means is that um, again, if you know calculus, you can actually use either L'Hopital's or degree approximations to, or any other method. There are more methods, but I just thought of L'Hopital's on the spot.
Ooh,
I actually don't know what a polynomial is. Okay. So a polynomial is, if I write this in summation form, is basically I from 0 to n of ai x to the I. That is a joke. The actual definition of actually, this is not a joke. This is the actual definition, but
yes, it
uh,
is.
it's even more complicated. But the actual definition of a polynomial is basically anything that has a degree. So like every term has some coefficient followed by some x followed by some degree, and that's basically a polynomial. And you add them, right? And the reason we need this is because every algorithm that any conventional algorithm runs in polynomial time. Usually it may run under polynomial time, but usually every conventional algorithm runs in polynomial time. Like if it doesn't run in, it definitely doesn't run in sine time, right? This won't make sense for an algorithm's time complexity.
No.
So it definitely runs in some kind of polynomial form, right? And how we can use the polynomial asymptotic rule, or the rule that's actually called something else, but I like to call it this, is that we can actually use the base form that OAX to the n equals OX to the n. Now the reason we can do that is that we don't care about the coefficient. Remember, because O time is basically the upper bound. What is the slowest time? And if we do that, we don't really care about the coefficient, because to us, 3x and 1000x is the same thing, because x can approach infinity, right? X can approach a gigantic value. Like you have algorithms that can run up to 10 to 100, right? Like that's how big some computers can run these algorithms. And then you might think that, oh, 3 and 1000, that's a huge difference. But when you have x equals to 10 to the 100, this is like 10 to the 3. This immediately becomes nothing. This thing immediately just becomes nothing, right?
Yeah.
Because you have these huge numbers that you're running on. These huge numbers. And we need this because computers, and in CCC, we also run on huge numbers. We don't run on, we don't have one test case or two test cases. In CCC, you have like, even with bad test data, you have at least 100 test cases. And each of these test cases have like thousands of values. So if you design a bad algorithm, you are not going to pass. In senior, it's even worse, because in senior, the algorithms are made to not work. So, but even if you're doing junior, or even if you're not doing CC, if you want to study any algorithm design, you need to know this, because you're running on these huge inputs. So
Mm,
the way you do this is that you basically get rid of all the coefficients, and that's how you do it. And then it's even crazier, because think about it. If I have x to the n and x to the n minus 1, so if let's say I have x2 and x1, which one do I care about? Anyone want to put in the chat? Would I care about x2 or x1? Remember, x can be like really, really big. Would I care about x2 or x1? X to the 1. Martin, is that why though? Why would I care about x to the 1? Martin, do you want to give an actual answer? Or is that your actual answer? If that's your actual answer, then because I can't tell if you're joking. If that's your actual answer, then I'll explain it. But otherwise, all right. Okay, I think he's not trolling. The actual answer is x squared. And the reason we want to care about this is that this gets so much bigger, so much faster than x to the 1. Remember, we want to care about the term that makes it really big because we want to make it small. Right? As x approaches a huge value, x squared goes up like this. And x1 is like, actually x squared goes up like this. And x1 is like, hey buddy, you want to slow down here? Right? It just gets asymptotically bigger. Like x squared and x are just so much different. They are just insanely different. Right? So we have to take the highest degree term. Otherwise, if we like Martin said, if we take what Martin said, we look at x1, then we ignore this huge term that gets really big. So imagine if we, to understand why we need to look at the highest degree term, imagine two things. Imagine we have like 3x squared plus 4x, and then we have like 10x squared plus, okay, this is bigger, this has to be smaller, plus x. And then we're like, okay, so let's look at this term, right? Let's look at x to the 1. And we're like, okay, so 4x is bigger, basically, so therefore this one is faster. But that's not true because x squared goes at so much faster than x, so the actual one that's bigger is 3. And it doesn't even matter if I put 400x1, right? I can put 400. I can put, or 44x. And you might say, oh, but 44x goes big, but not as fast as 3x squared does because we're running on huge inputs. So 3x squared becomes like, or actually, basically 3x squared is so much smaller than 10x squared, right? What I meant before is that 3x squared runs better, but 10x squared runs so much worse because it's so much faster. But if we look at 44x and x, we can't really see that because we don't look at the biggest term. So this basically means always look at the highest degree term. Another way you can do this is, again, to basically understand this, you can use mathematics. Again, you can use calculus, like you can use L'Hopital's rule to take care of any indeterminate form, and you can use degree approximations. Basically, if you're taking the limit of anything of x to the n plus x to the n minus 1, if x is approaching infinity, you immediately take out this x on n minus 1 term. And the reason for that, or the reason we do this in any indeterminate form or degree approximation, is that because x is incredibly big, when we study graphing, we see that this xn grows so much faster. Therefore, we only care about the bigger one. So we can actually use math to understand this. But again, if you don't want to understand it, remember one thing: always keep the bigger degree term. So let's do an example. Let's find the O. Okay, so let's first find the asymptotic growth of this. So before we even find O, omega, and theta term, before we even run into just doing that, let's first find the asymptotic growth for n cubed over 10,000. N is just x, it's the same thing, but programmers like to use x. Programmers like to use n, and mathematicians like to use x. I have no idea why that happens. Maybe it's just because people hate each other. But
We want to differentiate ourselves. Come on. We want to differentiate ourselves from mathematicians.
True. Okay. So what is the asymptotic growth? Oh, you have to leave. Oh, that's completely fine. Yeah. Thank you so much for coming. You can also read the listen to the lesson after, which should be recorded, so you can catch up later. All right. Cool.
Very important lesson
So
today.
yeah. So what is the? Oh, no problem. You don't even have to tell me if you want to leave. Just leave. I only care if Matthew leaves. I'm joking. I care if all of you leave, but you have to leave, just leave. Don't worry. All right, Martin, you want to tell me what is the asymptotic growth of this? Or anyone else? Not just Martin, but Martin likes to talk a lot. So Martin, you too. What is the asymptotic growth of this? Of this function or polynomial or whatever? You haven't taken grade 9 math yet.
Ouch.
Yeah. Okay. I mean, you can still kind of try to do this, right? Because all we have to do is we have to take the largest degree term, so the biggest number on the top, and then we basically get rid of the thing on the left. Yeah, this is also important because it's not just, you know, um, not just computer science. A lot of computer science is based on mathematics, especially the algorithm design of algorithms, because we're going to talk about this a lot more. Like when we talk about recursion, all we're going to talk about is this notation. Like it's literally just going to be how do we design, recursion to work for O(n) time and O log n. It's not as much coding as it is understanding how the algorithm works and how it runs under. Okay, so basically, Martin, how we would do this is that we would look for the number that's the biggest on the above the n. So the value that's biggest above the n. 3, 2, 1. Martin, which one's the biggest term? This is 0, by the way. If there's no n, then just don't ignore it. Which one is the biggest one?
Easy.
3. Yes, perfect. And then what do? We take this term and we delete the coefficient. So any number we delete. So what's the asymptotic growth now? So we delete this number. We basically take the highest degree term and delete it. Perfect. N cubed. Exactly. Great. That's the asymptotic growth. And what do? All right. Matthew, what is the big O of O(n) cubed?
Okay. Big O. I am very smart. I did not study this. It's been a while. I always did not like time complexity.
Okay, easy one. What is O theta?
Oh, theta. Oh no.
What is O theta? This should be easy. Because it's literally right here, but okay.
Yes, it's theta. Oh my god, it's
What
what
is?
can it be? It's n cubed.
Yeah, it's n cubed. What else could it be? It's right in front. N cubed. And then the O time is also n cubed. It's actually not n cubed. It's actually like by saying O(n) cubed, basically O(n) cubed actually means, if you think about it, as Cn cubed. Basically meaning that C can be any constant, so C can be any integer. But n cubed goes asymptotically faster, so we just care about the O. And we usually refer to O and theta interchangeably because, as you can see, they're not much different. It's just an extra constant. As we can see, constants mean nothing in programming. Oh no, phone. Okay, and then finally, I'm going to talk about the omega because it's kind of harder. But what this means is that the omega notation is now the smallest bound, and that is just n cubed over 10,000 because that is the term here. And again, we don't care about these terms at all because these terms mean nothing because n cubed goes asymptotically faster. The only thing that we kind of care about when we're talking about O, omega, and theta time is the constant because we still need to deal with that. But even the constant doesn't matter when we talk about big O time because immediately when someone says big O notation, you immediately know they don't care about the constant. The constant is just gone. It doesn't matter if it's over 10,000. It doesn't matter if it's you divide by 10,000, if you divide by 10 to 100, or if you multiply by 6. It doesn't matter whatever you get. Delete the constant when it's big O. All right. Up to here, if there are any questions, feel free to ask in the chat. And I think we will explain sorting and then just end there. Explain searching and then end there.
Yes.
Yeah.
You can do these exercises, I guess.
You can do them if you want. I'll put them at the end. Wait, let me pause my share for a second. I will actually take these and paste them at the end again. So
If you want to, you can redo these problems because some of them, I guess, can be a little complicated.
yeah, some of them can be a bit more complicated. For now, just look at this. How do I hide this slide? Oh, skip slides. All right, works. Yes. Okay. Some of these might be a bit harder, but it's completely fine. I'm sure every one of you is capable of doing this. All right. So let's look at the asymptotic growth of searching. So first of all, we need to look at linear search, right? Now we actually put what we learned in asymptotic growth to use, right? Because now we know that the linear search, what is the worst? Let's first of all, the best case. If I'm looking for 1 and I'm going from left to right, what is the O time that I find it? It's also written on the slide if you want. if you want to look at it. But even if you don't look at the slide, if I go from left to right, what is the O time that I find 1? What is the big O time for finding 1? Essentially, O.
Where would 458?
Okay. I don't know if that's a joke or like that's actually the complete. If O square root 458 is actually complexity. All right, Matthew, what would the complexity be?
Oh my god, it would be 001.
Yeah, exactly, because you search for it once and you immediately find it. Great. And then that's basically the worst case. And then the worst case would be ON because I'd have to find every element. Find every element. And how do I find the average case? Well, the average case is the best case plus the worst case divided by 2. And 1 plus n over 2 is, if you simplify, is 1/2 plus n over 2, which is, again, just n, because we take the highest term, which is n to the 1. We delete the coefficient, and it just becomes n. So that's the asymptotic time, is n. So O n. Now, binary search is the same thing, right? If you look for the middle and you immediately find it, then your best case is just 1. But what is the time complexity for binary search? And that's the last thing we're going to talk about, is that now we need to use all of our skills that we learned before about asymptotic growth of searching, the polynomial rule for asymptotic growth, and linear search asymptotic growth to actually find what the asymptotic growth of binary search is. It's going to be a bit harder, but we're going to get through this. And it's actually not super complicated. It's actually not. Surprisingly, it's not that complicated. And what we can use is something called a recursive tree. You might be confused. What is a recursive tree? What? I'm confused. And don't worry if you're confused, but basically you can visualize how to find the complexity of binary search using something called a recursive tree. This is recursion, but also technically not recursion because it doesn't need recursion. But we need to make an observation first. And the observation, you can kind of think about this, but I'm just going to tell you because I don't think you can think of it. It's really hard to think of it. It's okay if you can't. If you can, it's even better. But what the observation is that, what did I just do? Is that each step we're splitting values in half. That is our observation. Now you might think, oh, but isn't that just trivial? It is trivial, but there's something we really, really care about, right? Because when we split things in half, we're always splitting stuff in half. We are always splitting stuff in half, right? And what we can create is something called a recursive tree. And what a recursive tree is that at every single step, you're cutting in the middle and then subtracting into 2 smaller boxes. Cut in the middle, subtracting 2 smaller boxes. And at the end, somewhere after a lot of dots, actually, let me make this color black. After a lot of dots, you're going to come down to here, which is just a 1 by 1. And that's your base case. Basically, your base case is one you only have a 1 by 1. And why this is important? Well, this is important because at the end, we're always going to have a base case where you only have 1. Right? And we want to work towards that base case. We want to take ON, and then we're going to split it down, 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 and down until we only have a 1 by 1. Because that's when we're done, right? If we look for this element and this element is equal to our answer, then we're done. Right? And that's essentially what we're doing with the recursive tree. It's actually not exactly that. We're actually only searching in one of these two, but we are always splitting. So let me give you a concrete example. Let's say it's 1, 2, 3, 4. 3, 4, 5. And we're looking for maybe 4, right? So then first of all, we're going to say 1, 2, 3, 4, 5. Let's look in the middle, right? That's the first step of binary search. We're looking in the middle. And we split it into 1, 2, and 4, 5. That's not actually what we do in binary search. We're just doing it so then we actually design a better algorithm for binary search, right? We're designing the algorithm for binary search. And then what we say is that at each step, we divide by half, right? Because that's technically what we're doing. It's just not what you think that you're doing. And you do that, and then you get, because we're looking for, 4, we're looking for 4, right? So we know that because 4 is bigger, because we know that 4 is bigger than 3, so we look for 4 and 5. And then we see that this one is 4, this one is 5. And then we look for the smaller one, which is 4, and we found it. It only takes 2 steps, not 5 steps. Not 1 step, but 2 steps. And the way we did it is that we basically split each turn, split into 2, keep splitting, splitting, splitting until we have our answer of 4. And this internal splitting actually breaks every time into half when you only need to look at one of these halves, which means that at every time, all you're doing is that you're splitting into half. How many operations does that take? It takes one, O1, because you're moving it into two operations, right? You're basically splitting up the array and moving the pointers. You don't actually need to split it. What you're actually doing is that you're moving the pointers to 4 and 5, right? Remember, we have low, mid, high, right? Low is the lowest value, mid is middle value, and high is the highest value. We're just moving the pointers around. But at the end of the day, we're actually splitting into half. And that's how you can, recursive tree is how you can see this happen. With the recursive tree, you can actually visualize every step that happens. And all right, our final step now is that we need to figure out how we can do with this, right? So first of all, we're going to assume something. We're going to assume that n equals to 2 to the power of k. Assume that it's a power of 2. This doesn't degrade the problem. It just makes it easier to solve because now we know that we need to divide k times. Because after k times, this number becomes 1. Well, what is k? Because we don't know what k is. We only know that n equals 2 to the power of k. So we need to find k. What do? Well, we take something called a logarithm. All you need to do is that the logarithm moves all this k to the bottom. So what this means is that when you move this, you take the log of k, log of n, on the left side. And that's the right side becomes k, or 2 to the k becomes log k, log 2 to k. Or actually, no, it becomes k. What am I doing? Yeah, it is k. I had a brain fart for a second because I thought this said like k 2k to the 2 or something. So then I was like, wait, what? Isn't it log 2k? But no, it's 2 to the k. So if it's 2 to the k, you take the 2 and you move it to the bottom. So log 2n equals to k. And that's your answer. So basically, your time complexity is k because it takes k steps, and k is log 2n. And that is finally your value. Now, in computer science, log n almost always means log 2n. In math, it means log 10n, but it almost always means log 2n. If you want to make other people understand, a more a notation that's like more accepted is log n. It's literally called log n because log n basically means that there's two values, so it's 2 log 2n. Think of it as like lg, so two characters, so log 2n, and it's called log n. So basically, we can solve this problem in n log n time, or n log 2n time if you want to do that instead. And that's basically our average time too, because we talk about our average time or a best case, or actually our average case or a worst case is basically when we split every time and we move up. And that's our average time and our worst time. Right? And that's basically how we did it. We used the recursive tree and we used our asymptotic properties to understand it. And one more thing about induction is that this is really simple to the definition of induction. And that means that you have a base case, or your base case is O1, that's your base case. When there's one more value, that's your base case. And your inductive hypothesis is that you're making the general array smaller. You're taking this, you're making it smaller, smaller, smaller until it gets to 1. And that's basically induction. Okay? We can use induction in a lot more ways, like to induct on n when we're trying to use asymptotic, or to measure an algorithm, we can induct on each step. But basically, we're actually using the principles of mathematical induction without even realizing it. Because what we're doing in a recursive tree is that we're splitting in half. And that's a lot of when we're talking about recursion, we're going to look at, it's kind of the same thing, right? We're using induction here, and we're kind of using induction in recursion too. This is kind of a preview of what induction is, and also what recursive properties are. All right. So last thing is, I don't even, let me see what is left. Before I see what is left, does anybody have any questions? Feel free to ask in the chat. Yeah, that's pretty much it. All right.
Log. Ooh. Okay.
What is log? Okay. Okay. So basically what log is that it's when you take on, when you have a value of on, you can take the okay, so first of all, let's say you have 100. Log of 100 or log 10 of 100 is equal to 2. That's what log is. So what log is that basically, if you know what exponential form is that let's say you have 2 times 2 times 2, you can actually write it as 2 to the power of 3, and that's called exponential form. And then what log is that you convert this exponential form back into regular form, because if you can take this notation, you have to have an opposite notation. So it's the opposite of exponential form, right? So if you have log 2 of 2 to the 3, you just have 3. Basically, you're taking this number up here. If this base matches up with this number, you just take this number up here. and you're converting a number that was once exponential form to decimal form. Yeah. Coolio, yes. And also, one more thing is I want to talk about some graphs, and here are some more complicated algorithms that you might encounter. So maybe you have stuff like 2 to the n, which is again basically this is called exponential time. So 2 to the n is basically 2 times 2 times 2, and you do that n times. And then you also have stuff like O log n, which is what we talked about today with binary search. And yeah, and here's the code for binary search. It's really simple if you understand it. It's really, really simple because the crux of binary search is understanding why it works and how fast it is, and not really the code for it, because that's way easier than understanding the crux of it, right? So you take a low and a high and a mid, like we talked about, or yeah, a mid, and then you basically each time you split in half, and then you look for a lower value and a higher value, right? So if mid is less than secret, we're going to set low to mid plus 1, which means that we're actually going to remember our recursion tree, right? We split it into 2 different arrays, and we actually take the array on the left if it's less than secret. If it's more than secret, we take the array on the right. And then when we get it, we just say that we got it. Yeah. And here are the exercises again. So if there's time, we could also go through just the time complexities and asymptotic notation again. And yeah, here's a practice problem for binary search. Before we go, maybe we can, before we talk about the final exercise, I'll just do one more like really quick talk about everything that we talked about. So basically, first of all, we talked about asymptotic growth. So asymptotic, this is just a overview of what we talked about because this is really important. We're starting next lesson, we're just going to immediately just jump into like big O notation. Like if we say O n log n, we're not going to explain what this kind of means. Like if we say n log n, we're not going to explain, we're going to explain why, but we're not going to explain what this means. And this basically means that it takes n times a log n, right? So basically this, when you see O, you should know what it means. We're not going to explain what O is. We're going to explain what this is though, but not what O is. So next time when we see O or theta or omega time, you should know what it means, right? So again, any CRUD operation on a CPU takes theta 1 time, and then we take a lower bound and upper bound, but we only care about O because again, it can't get any worse than O. O is bad, can't get any worse than this. And then we defined a rule, a general rule for polynomials, right? So basically polynomial asymptotic growth, and it's called a polynomial asymptotic rule, which basically states that first of all, if you have a coefficient, it's gone. We don't care about coefficients because in the field of computer science, we're dealing with numbers that are gigantic. They are gigantic. So you don't care. You just throw it out. And same thing with the polynomial. N squared grows so much faster than n that you don't even care about it anymore. Right? If we graph it out on Desmos, which I can actually show you too, let me, because we have a bit of time, I can actually show you on Desmos. So this is Desmos. And if we look at y equals to x, this is linear time. This is how fast it grows in linear time. And then we see the other one, which is y equals to x squared. And it's like, holy, this is really big. And then if we take an even bigger one, we say y equals to x cubed. These 3 are insane. Like, look at how fast this one is growing. This one is just growing insanely fast. Now, if you look at this, here is the final picture in which all 3 are still in the picture. These 2 are kind of close, but this one and this one is so far off, right? Like x2 and x cubed are just way far off, like way, way far off, which is really important to look at it because if you look at it like here, because a lot of people have tunnel vision and they start looking here, and they're like, okay, but if the numbers are small, x cubed is the slowest, so therefore x cubed is the slowest. But that's the worst way to do it because if you get tunnel vision, a lot of people do this. They have tunnel vision where they look at this. And you don't even realize you're doing this. But the important part is to look at the big picture. Go back and look at Desmos, right? Graph out the function and see which one is actually faster, not the one that you think is faster, because the one that you think is faster, you might just be zooming in on this. And you might just get the order completely wrong, right? So that's a way you can actually visualize how fast it's just going. And you can also use Desmos because this is in a math class. So no one cares if you use Desmos or not. It's great. And here's some exercises. basically we can find, first of all, to find this, you would find the asymptotic time by taking that and deleting. And now you have the omega time. To get the O time, you basically find the worst case, which is C log, which is Cn cubed, which is the same thing as just n cubed. So O and omega are the same thing. That's why most programmers just call them the same thing. And theta is basically n cubed over 10,000 because you keep the notation, because theta is a lower bound on upper bound. And then we talked about this too, these two too, and then how can we prove and find time complexity? We talked about that, which is asymptotic notation, so polynomial asymptotic growth and big O time. And then we talked about the asymptotic growth of searching, and the linear search is really easy again because we can kind of understand, we can go through the element and say that, okay, we're either searching every element of the array or searching one element in the array. And then we do some math like we talked about before, and we have our thing. But with binary search, it was a bit harder. So then what we were like is, okay, let's define some kind of tree that we can work with. So we define a recursive tree, and the recursive tree comes from the observation is that in each step, we are always splitting values in half. And then we create this recursive tree because we're splitting every value in half. We're always doing that, right? And then we say that how do we define this algorithm? Well, look at this. This is n. This is n over 2. And this is n over 2 squared, right? So every time we're just dividing by 2. Actually, this is actually the floor function too, because you're actually flooring this. But this is a technical math part. You don't need to worry. All you need to know is that you're dividing by 2. So let's make n equals to the power k to make it easier. When we take log of both sides, right? So log is basically the opposite of an exponential, right? Because we keep dividing. When we divide or multiply multiple times, it becomes an exponential. So to figure out how many times we have to use log. And when we do that, so we have n equals to 2 to the power k. And this is the most important step. When we take log to both sides, we have log n, or log n equals to k. And that's it. And that's our answer. So that's our O time. And if you, this is also really important, random plug, but shameless plug, but math is important too, just like CS. All right.
Very
And
important.
then, yes, notes on induction. And yeah, that's it. Here's some graphs, here's binary search, here's some exercises, and here's a practice problem. Any last questions? Any last questions? All right. Let's see. Does anybody have any more questions?
Doesn't look like there are going to be any more questions. So
Proof by AC is best. Yes, that is. That is very true. But also,
yes.
if you can't prove by AC, it might be because you're not understanding the algorithm. Like if you can prove by AC every problem without understanding the algorithm, good for you. Right? That's really good. You're probably like Josie Xiang. But if you're not, then maybe you have to think about, should I learn asymptotic growth, or should I try to understand the time complexity of every algorithm instead of just blindly tunnel visioning on or just blindly tunnel visioning on everything else. Is everybody? Who else is done? Oh, okay. So
Well,
Ryan's was done. Okay.
I
Yeah.
guess.
Instead of tunnel
Not
visioning, you
done.
should try to understand asymptotic growth as well. Instead of
Okay.
tunnel visioning on which one is faster based on just different arrays. Were you gonna say something? Matthew?
No. Well, anyway, I think basically the lesson's over now. So thank guys for like listening to our lesson and
Yeah.
stuff, and make sure to tune in next week for our next lesson.
Yes. Please tune in next week.